Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Vishal Chatrath, CEO and co-founder of QuantrolOx, a company that uses machine learning to automate the tuning of qubits and gates. Vishal and I talk about his journey from combustion engines to qubits, the rate at which their continuous optimization works, whether quantum computer manufacturers will develop their own calibration, and much more. We hope you enjoyed this episode.
Hello, Vishal, and thank you for joining me today.
Thanks a lot for inviting me, Yuval. Very nice to be here. I'm a big fan of your podcast, so I'm really honored to be here.
I appreciate you saying that. So who are you and what do you do?
So my background is really from the technology side. I entered the tech industry after graduating from India in 1995. My first job/research scholar was at the National University of Singapore. So I worked on 3-5 semiconductors. And in those days, trying to do something that we call the quantum wells among various things. Then in 97, I thought this so much material research wasn't for me, so I jumped onto the industry. I didn't know all these years later I would come back to quantum. So I worked in manufacturing in Singapore for a while. Then I moved to North Finland, worked for Nokia for many, many years, variety of roles, operations, mobile architecture definition very early, business development, corporate strategy. That took me to many different places around the world. I lived in 6 countries, I think about 11 cities by now. And the common thread always was to work with very early stage technology. And that's really my comfort zone, something that's fashionably called as deep tech today. And I've been an entrepreneur since 2010 with varying degrees of success and learnings. And my previous 2 startups were linked to University of Cambridge, both in AI and machine learning before it became fashionable. And started QuantrolOx in 2021. I was invited by Professor Andrew Briggs to his team. And Andrew was one of the pioneers of the quantum program in the UK. And the other 3 co-founders with me, Professor Natalia Ares and Dominic Lennon, is also from the University of Oxford. So they are the people with a physics background, and I am this so-called industry guy trying to take the company out, take the science to technology, and build a viable business.
And what does the company do?
So what we focus on is trying to develop machine learning-based software that automates the tuning of qubits inside the quantum computer. So as we all know right now that qubits are highly, highly unstable as compared to your bits in the normal like classical computer. And qubits don't like to stay where we want them to stay. And if you look at your typical superconducting or spin qubit based quantum system, you require 2 to 3 researchers to literally babysit it, kind of just to keep it alive. And we'd rather have these very smart physicists rather than being there trying to babysit the systems, doing something useful. So our automation software will hopefully bring about complete hands-off, keeping the things alive by themselves. Think of it as an autopilot for the quantum computers.
How does it work? Does it think about the quantum computer as a black box, just runs some tests as if I were a user and measures the results? Or does it do something else? Please, whatever you can explain.
Yeah, so that's a very good question. I'll keep it at a slightly higher level. So what we do is we take the readouts from the quantum computer, and at microsecond intervals, we make the decisions, which essentially, among various things, tell the AWG, which is the arbitrary waveform generator, what is the shape of the pulses to send back to the quantum computer. And we are making these decisions at microsecond intervals. So it's a very fast closed loop, automation that learns in real time from the status of the machine. We've been testing these ideas and algorithms in the university environment for maybe the last 4 or 5 years, quite successfully with spin qubits. And the first product, which we previewed at APS March this year, and will be launching at SQA, which is the Superconducting Qubits and Algorithms conference on 29th of August. And it'll come integrated with a few different control hardware types, including Q blocks, quantum machines, Zurich instruments, and a few others.
Given that it's microsecond resolution, is that a software product or a hardware product?
It is a software product, and that's a very good question that you ask. So our integration is very much close to the actual, the kind of a lower level integration to the hardware, and I think that also makes us different from some of the other companies that are trying to do control software. But they do tend to come in from the kind of higher layers like Qiskit and so on and so forth, where we are connecting and talking to the control hardware at the FPGA level.
Would a quantum computer manufacturer, wouldn't they develop their own control software and own optimization software, or do you feel there's a need for more of this componentized approach?
I think that's a very good question, and because I love technology and I also love history. So if I look at the birth of any industry, in the absence of a supply chain, in the beginning, everybody builds their own things, right? So if you look at IBM in the 1970s, there was no notion of BIOS, hardware, application layer, UI layer, and so on and so forth. It was just one monolithic stack where all these fine layers were not there. It was only in 1984 somewhere around 1984, when IBM came up with the MDS architecture, which started to kind of differentiate out these layers. So for the really big ones who can afford it, like the IBMs and Googles, for all the right reasons, they are doing everything in-house. But there's this huge market out there of people who are not building their control hardware, are buying it. And I think that's the market we are going to address to also give our control software. Because there is just too much to do. And there are many companies who are trying this fully integrated, full architecture approach. But you can already see, unfortunately, from the market cap of the not Googles and the not IBMs, that it is a very expensive game. And people have to open up their architecture to be able to succeed and compete. Yeah.
Is the technology optimized today or specific to one type of qubits or a couple types of qubits, or is it more universal in nature?
So at least in theory, it should be applicable quite widely. But so far, we have only tested it for spin qubits, which was our history, and now for superconducting qubits, and it works very well for both. Because we are a small startup, we are only 18 people. In the beginning, we will not go out to every market. We are very much trying to build a viable business. So wherever the market volume is, we go after that. So hence the first product is for superconducting qubits because the market volume.
Is this essentially a real-time calibration, or do you take up a certain percentage of the availability of the computer to run periodic calibrations?
So the software works in kind of real time and all the time, because I think there is so much happening in the environment. So we are taking into, I think there are about 40 parameters we are taking into account while trying to keep these qubits alive. And it is real time, but as an absolute engineer, you might argue that actually what is real time. So I can tell you at microsecond intervals, we are making the decisions, and the software just runs all the time to keep it alive.
I assume the desire is to scale to hundreds or thousands or more qubits. How can you run this for something with microsecond intervals and have thousands of qubits? You're going to need a little supercomputer to run the calibration all the time for all the qubits at these kind of intervals, wouldn't you?
I think yes, we will need like a quite good enough machine, but at the same time, there'll be also quite a few smarts on the software side. So, for example, right now, because we don't have access to any chip that's over, I would say, 20 or kind of qubits right now. We hope to get more and more heavier chips. But also for a 20 qubit chip, even at that scale, you have to do some parallelization of the whole work. Because if you try to do it in a serial order, even 20 qubits, the whole tune-up will take a very long time. So our goal is to be able to finish the tune-up from scratch in a few minutes.
For the real-time tune-up, it sounds like you might essentially be tuning the qubit in the middle of the program. While the program is running, if I have multiple operations, then the first operation might have, qubit tuned to one parameter, and then later on to another one, given, as you mentioned, the microsecond interval. Is that correct?
Okay. I think in that sense, I think now you kind of bring it up to a good point. So obviously, for the period in which the compute is on process, then the goal is not to touch them. But once the compute is over, then to kind of bring it back to the same speed. So I think I probably kind of overstressed the point, but I think you are very accurate with your kind of description that as and when somebody wants to run a compute, it is available. Because right now, and I've been kind of talking to one of the industry leaders here, the state of the art is that it's actually a human. So if they want to run any kind of a 10 qubit, then there's a human who goes and tags the kind of a 10 best qubits inside a QPU, and then they run the compute, and then he or she will shout across the room that, okay, all is good, and then they will kind of click enter and the program runs. So we are trying to automate that entire loop.
I think historically computers were calibrated every couple of hours or maybe even every couple of days, and then between that and the next calibration cycle, the performance would decrease. And you're doing continuous calibration. In your experience, in your testing, how much better does it perform than calibrating the machine once in a while, even if it were once every 5 minutes or once every couple of hours?
We don't have any kind of results that we can talk about yet, but I think that's something that, after we do the product launch in the fourth quarter, I think that's a good time to actually talk about it. What we have kind of definitely seen is that the calibration is obviously much faster than a human. And also our first goal is to not focus on the qubit quality in itself, because at the end of the day, we can just drive the qubit to the ultimate capability of the QPU itself. Our goal is, at the first instance, to speed up the process. And once we speed up the process, then work on the quality metrics. So it's kind of two different parts we are driving.
Some optimization tools understand that not all qubits are the same. Some are better than others, maybe based on manufacturing variances or others, and then work to optimize the program to make sure that the best quality comes out. Does your software provide information to allow that software level optimization of the program itself?
Yeah, so there are two parts to it. So the first part is, obviously, our software is very much sensitive to the individuality of the qubits, and we have some research papers on our website. One of the key papers was where we showed that for 3 completely different silicon germanium spin qubit architectures, without any changes in the software, we were able to learn the kind of intricacies of the devices and be able to tune them automatically. What we don't have yet in the first phase is a link between the need of the state of the qubit depending upon the algorithm, because there's also some field of work going on that for a certain algorithm type, you will need the qubits to be at a certain state to be able to execute it. So that's the plan for the future. And while we are working in the first stage for integration towards the control hardware, in the second phase, probably sometime in 2024, we'll start to work on the integration of our software basically upwards. So that's the kind of open chasm layer where we want to make the link between the needs of a particular algorithm and to ensure that the qubits are automatically driven to the stage. Yes.
And when you say optimizing qubits, I actually assume you mean optimizing gates, right? It's not
That's
just
right.
the qubit, but
That's
the
right.
2-qubit gates.
That's right.
Because
Because
2-qubit gates, yeah.
no, you're absolutely right. I think that's what I mean. But I guess because in our head, we are so much focused on the qubits itself. And the goal obviously is to automatically get to single qubit and 2-qubit gates as defined by the higher layers.
You mentioned that you use AI and machine learning to do this. Machine learning today is an overused term. Everyone wants to attach AI or machine learning to their product to make it seem smarter than it is. To what extent is it really machine learning as opposed to just a smart closed loop, system control?
So I think it is a lot. So our focus mainly is specifically on Bayesian optimization, and we use this Gaussian processes and Bayesian optimization for that. And I have a bit of history with that kind of machine learning and not really deep learning. So the previous company which I founded and I was the CEO for 5 years was a Second Mind, where we used similar techniques also for the tuning of internal combustion engines. So in that case, it was a 13 parameter state space. And again, because the cost of data acquisition is so high, we simply cannot get the amount of data that you require to use deep neural nets from a quantum computer or from an internal combustion engine. And here, therefore, the team and myself and our CTO, we have a very kind of good background in applying those very efficient approaches.
From combustion engines to qubits, that's an amazing journey.
It's still tuning.
Absolutely. Do you need special feedback, special data collection inputs from the quantum computing manufacturers? Do you go to a manufacturer and say, well, look, if you could give me XYZ parameters, we could do much better tuning?
Yes, of course, that helps. So I think also as far as the company is concerned, and especially in this, the environmental, so when you use Bayesian optimization, the modeling of the environment has to be right, because if you get the wrong model of the environment, you're going to get all junk. So we've been very fortunate that one of my co-founders, he when he did his PhD under Natalia's lab, so he had really focused on being able to get these machine learning techniques and quantum physics in the same brain. So in that sense, yes, we do have a very good understanding of the actual, the physics that we are dealing with. And we, of course, work very closely with Quantware, and QBlocks and quantum machines and Turing instruments to ensure that we have the deep understanding. And the other thing to remember is that we are all experimentalists. So all the machine learning techniques that have been developed over the last 5 years were not done in some simulation environment, were actually done inside a lab. And Natalia's lab has had 5 dilution fridges. So we are very much kind of hands-on. So we know what works and actually what doesn't work in real life. Yeah.
Some vendors say that they can use the same techniques that they use for qubit optimization or gate optimization to also optimize quantum sensors. Do you see it the same way? Would your approach be applicable to quantum sensors as well?
I think, again, it depends upon what you're using to build the sensors. So these days, most of the sensors that I hear about are using, ion traps and, cold atoms and so on and so forth. And any of these, laser-based approaches, we don't have experience. Again, in principle, it should work, but in practice, we have not tried it. So our experience is only with any sort of microwaves.
What can you tell me about the company in terms of size, funding, what you're looking for, location, anything you can share?
Yeah, so we started the University of Oxford, and we have two main locations. One is in Finland and one is Oxford. We are about 19 people now, almost 50-50 between Finland and Oxford. We have raised about slightly over 5 million in terms of venture funding. We've gotten over 3 million in terms of various grants from EIC, UK and Finland. And right now we're in a very exciting place where from day one, we've been working very closely with the industry. So I believe we are one of the first companies to focus so much on end user research. So when, for example, we were thinking about the first product, because I come from a product development side, I really wanted to understand the day in the life of a quantum scientist, because we knew that part of the improvement that we bring will come from our smarts. But I also observed that any typical quantum scientist, in order to control the quantum computer, was jumping anywhere between 35 to 40 different windows, right? And to me, that didn't sound very operationally efficient. And we thought, can we bring in software that constricts everything and solves the problem down to one window? So we really think about a lot of these parameters. So because we've been building these products so closely with actual quantum computers, we believe that when the product is fully released at SQA in the end of August, we are quite confident it'll really solve some real-world problems. And what we would like, we would love people in research labs, in academia, in companies to really try our software and actually give us feedback. And that's the only way to build a outstanding product. What we do want to be is we want to be the de facto sort of control software layer, or at least we want to work towards trying to create some de facto interfaces. And we are again very much keen on this whole open architecture approach, which we believe is foundational to scaling of the industry.
As we get close to the end of our conversation, I'm curious, what have you learned over the last 6 months that you didn't know prior? What's new in your world or in your view of the quantum world?
Well, first thing is that after dealing quite a bit with dilution fridges, so we have actually realized that how easy they stopped working. So how much more automation is required. So far we've been focusing on the automation of qubits. I think eventually we'll have to get to the full end-to-end automation of the entire quantum computer. And I think our focus has also changed, ambition has changed. So now I see ourselves as an end-to-end software for, as I mentioned, controlling the entire quantum computer. The parallel that I can bring in from my world of manufacturing is that when I first entered manufacturing, you had about maybe 10, 15 machines in the production line, and each machine had its own computer to optimize that machine. But you also had this software that controlled the entire manufacturing line. So I think there is a need for that, and eventually we see ourselves becoming that.
And a hypothetical question, if you could have dinner with one of the quantum greats, dead or alive, who would that be?
So that's a very good question. The thing that really got me excited about quantum physics in the first place was a book that I found in a bookshop called Surely You're Joking, Mr. Feynman. And I was a teenager then, and that's the time I realized that you could do physics and have a lot of fun. And so it has to be him. And I would just talk to him about his life. And if he still has time to take me through at least one of the Feynman lectures on quantum mechanics, because, that's what I really kind of grew up with. Yeah.
Vishal, thank you so much for joining me today.
All right. Thank you very much, Yuval. It was a joy.